Hi, this is Jin Yuan Chen. What I'm going to talk is focusing on solving an open problem of Byzantine agreement by using tools from coding theory and graph theory. Byzantine agreement as originally proposed by Pease, Shostak, and Lampo in 1980 is a distributed consensus problem where end processors want to make the consensus on the L-bit message or value, but up to T of the processors are dishonest or faulty. To solve the BA problem, the protocol needs to satisfy the conditions of termination, consistency, and validity. In a different area, coding theory is a powerful tool for error detection and error correction. It has been used in many applications such as data compression, data transmission, and data storage. In this talk, we will show how to solve the BA problem by using tools from coding theory, together with graph theory and linear algebra. We will focus on the deterministic BA problem without authentication. The quality of the BA problem is measured by three important parameters: resilience, row complexity, and communication complexity in bits. The row bounds on those three parameters are T plus and 3T plus 1, T plus 1, and the maximum between NL and LT, respectively, where L is the size of the message. Focusing on the binary case of the BA problem, the protocol proposed by Pease, Shostak, and Lampo in 1980 achieves the optimal performance in resilience and row complexity, but the communication complexity is exponential. After more than 10 years of improvement, the protocols proposed by Berman and others, and Cohn and others, achieve the optimal performance in resilience, row complexity, and communication complexity, but again, just for the binary case. In practice, the consensus is often required for the multi-value message rather than just single-bit message. For example, in blockchain system, the size of the block message could be a scale around 1 megabyte. Focusing on the multi-value BA problem, Liang and Vaidya in 2011 proposed a nice protocol that is optimal in resilience, but there is a cap in the row complexity and communication complexity. The result by Liang and Vaidya was improved recently by Ganesh and others, Lovelace and others, and Nizar and others. But again, there is a gap in the communication complexity. This is an open problem. In this talk, we will focus on solving this open problem. Let's begin with the naive scheme. The multi-value BA problem can be solved by invoking L instance of the 1-bit consensus in sequence. But this scheme will result in a communication complexity of n squared L bits, which has a large gap compared to row bound. The scheme we just mentioned can be considered as the scheme with full data transmission. Since the processors need to exchange the full data, it is not surprising that this scheme results in a high communication complexity. To reduce the communication complexity, one possible solution is to let the processors exchange only one piece of the data instead of the full data. But this protocol might lead to a consensus error. This is because the processors might not be able to learn enough information about the initial message. So the protocol is not robust against the Byzantine attack. If the data is encoded with error collection code, the processors might be able to detect and correct errors, even with reduced data transmission. So this protocol might be robust against the Byzantine attack and could be error-free. Our protocol is a coding solution. The advantage is that the communication complexity can be significantly reduced, but there is a challenge. In a coding solution, the processors exchange the encoded and compressed information symbols, where the information symbol is the projection of the message on the encoding vector. The challenge is that the encoded symbol could not reveal enough information about the initial message, which might lead to some illusions at other processors. For example, when one processor initially hold a message as W1, when this processor sends out the encoded symbol projected from the message W1, this encoded symbol might seem to be projected from the message W2 when W1 minus W2 is in a null space of the encoding vector. In this case, it creates some illusions at other processors that this processor might initially hold the message as W2 but not W1. Our goal is to control the number of illusions to be small by using graph theory and linear algebra. To control the size of the illusion to be small, at first, we classify n processors into different groups. The group AL denotes the indexes of the honest processors having the initial message as W1, WL. The subgroup ALJ is the subset of AL such that the encoded symbols sending from this subgroup seem to be projected from the message WJ, but actually projected from the message WL. For example, for the subset A12, the encoded symbols sending from this subset seem to be projected from the message W2, but actually projected from W1. Similarly, the encoded symbols sending from the subset A21, A31, and A-eta1 seem to be projected from the message W1, but actually not. Our goal is to control the size of all of those subsets to be small by using graph theory and linear algebra. Specifically, the parameter eta is controlled to be small by using graph theory, and the size of each subset is controlled to be bounded by using linear algebra. This is the high-level insights of our protocol design. For the multivariate BA problem, this is our main result. What I say, it says that the proposed protocol Q achieves the optimal resilience, optimal route complexity, and the optimal communication complexity when the message size is bigger than or equal to T log T. Our protocol is a deterministic protocol. It is correct in all the executions, and it does not depend on authentication technique. Furthermore, it is secure against the computationally unbounded adversary. In this BA problem, we also introduced the notion of communication complexity exponents, message size exponents, and the faulty size exponent given by those forms. As we can see that our protocol achieves the optimal communication complexity exponent. This table provides the comparison between our protocol and some other error-free BA protocols. As we can see that communication complexity is improved. In the following, we are going to show the design protocol. Our protocol has 4 phases. At the end of phase 3, we can see that at most one group of honest processor have their updated message as non-empty, the rest have their updated message as empty. We also can see that the size of this group is larger than the size of the faulty group, such that in phase 4, we can calibrate the message of the remaining honest processors to have consistent consensus. This is the high-level insights of the protocol design. Let's look at the protocol phase by phase, and we look at the protocol from the view of processor I. The goal of phase 1 is to exchange the complex information and learn it. At first, process I encodes the initial message into n blocks by using resolvent encoding. The design of the parameter K and C is one of the key elements in our protocol design. After that, process I broadcasts a pair of coded symbols to each of the other processors. Then, based on the received observations and its own observations, process I will set the link indicator, and then process I will set the success indicator by checking this condition. After that, process I broadcasts the success indicator to other processors. And then based on the received success indicators, process I creates the set of the true success indicators and the set of the false success indicators. The goal of the second phase is to mask the errors from the honest processors. If one processor has the success indicator as 0, it means that the encoded symbols sending from these processors cannot be trusted. So the link indicator connected to this processor needs to be updated. Once the link indicators are updated, process I update the success indicator as in phase 1 and broadcast it and update the set of S1 and S0 as in phase 1. The goal of the third phase is to mask the remaining errors from the honest processors. Process I will update the link indicators and the success indicator as in phase 2, and then broadcast it and update the set of S1 and S0 as in phase 2. After this step, process I will vote by checking this condition and run the 1-bit consensus with other processors. If the 1-bit consensus is 1, process I will go to phase 4. Otherwise, process I will output a default value, say empty, as the final consensus and stop. Phase 4 is taking place when the 1-bit consensus is 1. At first, process I updates one encoded symbol by using the majority rule. Then process I broadcasts this updated encoded symbol to other processors. Based on the updated encoded symbols, process I will decode the message. In the final step, process I output the final consensus with the updated message. In our protocol, the communication happens in those steps. One can check that the communication complexity of this protocol is the maximum between NL and anti-lock T. Regarding the raw complexity, it is dominated by the raw complexity of the 1-bit consensus, which is in the order of T. In the following, we are going to analyze the protocol in terms of termination, validity, and consistency. We can tell that all honest processors eventually terminate together at the end of phase 3 or at the end of phase 4. So the condition of termination is satisfied. If all honest processors hold the same initial message, in the first 3 phases, all honest processors set their success indicators as 1s and keep the updated message exactly the same as the initial message. In this case, all honest processors go to phase 4 and output the final consensus exactly the same as the initial message. So the condition of the validity is satisfied. One key step for proving the consistency is to prove that at the end of phase 3, at most, one group of honest processors update their message as non-empty. The result is summarized in this lemma. This lemma says that at the end of phase 3, at most, one group of honest processors update the message as non-empty, the rest as empty. In this way, in phase 4, we can calibrate the message of the remaining honest processors. The proof of this lemma is based on 2 important results. The first result is about linear algebra. It says that each subset is bounded by K. The proof schedule is given as follows. In the first step, we construct a set of the linear equations represented by this form, where the matrix is full rank with psi m by k, and the vector is with dimension k. We argue that if m is bigger than or equal to k, the only solution to this equation is that the vector is 0. If the vector cannot be 0, it must be true that m is less than k. This argument gives this result. The second result is about graph theory. We focus on a specific type of the graph satisfying these 2 conditions. One of the examples is given by this figure. The right-hand side is the 3-layer representation of this specific example. In this specific type of the graph, we have a specific vertex I star equal to 1 in this case. We also have a specific set C, such that each vertex in the set C has at least n-2t edges. And we also have a specific of the set D, such that each vertex in the set D is connected with at least k vertices in the set of C. Given this specific type of a graph, we show that the size of the set of D is lower bounded by this number. The proof schedule is given as follows. In the first step, we consider an extreme scenario with the minimum size of D for this specific graph. satisfying these two conditions. One example is given as follows. We have a specific scenario with a large size of D. Then we can transform this scenario of the graph to another scenario of the graph with smaller size of D, satisfying these two conditions. Then we argue that the number of the edges connected to the set of C is given by this expression. And then we argue that minimizing the size of the D is a game of allocating this number of edges between the set of D and the remaining set. This is a high-level proof schedule for this graph theory lemma. The proof of the consistency is taken place for each of the two cases. In the first case, the consensus of the n votes is 0. In this case, all honest processor output the consensus as the default value, so the consensus is consistent. In the second case, the consensus of n vote is 1. In this case, we argue that at least T+1 honest processor set their success indicators as 1s. And then with the previous result, saying that at most one group of honest processors having the updated message as non-empty, the rest with empty. Equivalently, the success indicators are equal to 1 for this group. By combining these two results, we can make the conclusion that the size of this group is larger than the size of the faulty group. In this way, in phase 4, we can calibrate the message of the remaining honest processors. So we can show that all honest processors output the same message. At this point, the consistency is proved. Okay, in this talk, we show how to solve the BA problem by using the tools from coding theory together with graph theory and linear algebra. We show that the coding solution with reduced data transmission is a good solution in terms of the communication complexity and the correctness. Our protocol can be extended easily to the Byzantine broadcast problem with the same performance. Our approach can be extended to the asynchronous distributed consensus problem, the authenticated distributed consensus problem, and approximate a consensus problem, and so on. With this, I complete my talk. Thank you for attention.